Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to today's lecture. We have been studying the topic of measure concentration. Just to recapitulate, we saw Markov inequality, Chebyshev inequality, Chernoff bound. Chernoff bound provides a framework for getting good estimates of tail probability. Then we derived Chernoff bound for Gaussian random variables. Therefrom, we generalized the notion of Gaussian to sub-Gaussian. So, we are trying to describe a sub-Gaussian family of distribution, not explicitly specifying the distribution, but by constraining the behavior of the moment generating function. You know, moment generating function and probability density functions are one-to-one mapping of each other. Both contain the same information. Moment generating function from moment generating function we can compute all the moments. Please understand the trick in obtaining the concentration bound relates to controlling or finding bounds on various moments. So, with that in mind, we defined an extension of Gaussian to sub-Gaussian. Then we gave examples of sub-Gaussian bounded random variables, red marker random variables, and so on. Then we found out that the requirements on the parameter lambda in the definition of sub-Gaussian is that it can be any real number. And that constrains the other parameters in the exponent, because your lambda can be large, other parameters have to be, cannot take arbitrary large values. So, we want to be able to explore the ranges of parameters for which these things can be applied. We wanted to restrict the range of parameter for lambda to a smaller interval. That gave rise to the definition of what is called sub-exponential. Sub-exponential family of distribution, sub-Gaussian family of distribution. The example of a sub-exponential is chi-square distribution, which is the square of the normal distribution. So, this was the theory. The theory is very good, and you get to understand applications of standard techniques in manipulating moment generating functions. It's a very good exercise. It's an important exercise for those of you who are serious about data science. Then, towards the end of the last class, we started the study of an application of the sub-Gaussian type of bounds. To that end, we started with an example of a chi-square, and that gave rise to an application called Lindenstrauss lemma or Lindenstrauss embedding. This is where we started. Now, I am going to do a little bit of an overlap. Let us assume that I have n points in a d-dimensional space, d is large, n objects in the d-dimensional space, d is very large, and it requires too much of space to be able to store data. So, we would like to be able to seek a dimension m and a mapping f that maps Rd to Rn, where n is much less than d, and preserves some of the essential features of the data by storing only the mapped values of u1, u2, un according to the map F. Now we would like to look at this. This is Rd, this is Rn, this is u, this is f of u. So there is a mapping F that comes from Rd to Rn. So we call the distribution here, we can compute the corresponding distribution in here. So Rn is the host space where the the capital N points are the guests. When some guests come to our home, we simply say, please feel at home. So same thing we are going to talk about. This aspect of being able to squash the dimension from a larger space to a smaller space mathematically is called embedding. That's why it's called Lindenstrauss embedding. We also saw that if I have a triangle, equilateral triangle in a 2D, A, B, C, and try to map into a 1D, we can preserve the distance AB and AC, but we cannot preserve the distance between B and C. This essentially tells you the property of pairwise distances cannot be preserved when you map points from a high dimension to a low dimension. This is a fundamental difficulty of nature, and that's exactly what we are looking for. Any mapping that preserves the pairwise distances in the original space as well as in the mapped space is called isometric embedding. It's called the isometric embedding. Since it is not possible to have an isometric embedding by virtue of this counterexample, we are willing to relax the condition. The condition is given by equation 26. This is the square of the distance between the images in the Rn space, the smaller space. This is the distances between the same two objects ui and uj. So this is the image of ui, this is the image of uj. If delta is small, in between 0 and 1, 1 plus delta upper bound, 1 minus delta lower bound. This means the distance between the images doesn't differ too much from the distance between the original two objects. So for ui not equal to uj, if the inequality 26 holds good, for n much less than d, we call it near isometry. 26 is called near isometric embedding, as I talked about. Now we want to talk about, we want to describe the solution. How do we realize 26? Please understand, this has a couple of important implications. We are going to save space in storing data, so that's a kind of a compression. Secondly, we are also going to be preserving, very nearly preserving, the pairwise distances between the objects. Why pairwise distances is very important? That is because clustering, finding similarity between objects, is one of the important tasks in classification methodology. In other words, all the classification methodologies depend on some measure of similarity. Distance is a measure of dissimilarity. Smaller the distance, they are similar; larger the distance, they are dissimilar. Therefore, distance is a very fundamental and important property in classification. So we should be able to classify the original objects in the d-dimensional space by mapping them into a smaller dimensional space. And since we have not changed the distances too much, we should be able to preserve the distinct classes of the original data even in the mapped space. So it's a win-win situation. storage is less, near isometric condition implies the distances are very nearly preserved. We would like to be able to take advantage of these two factors. Everything depends on the design of the mapping F. So we would like to be able to now talk about how to realize 26 with a very large probability. So this is the concept of probabilistic algorithm. In other words, the near isometry we have to establish not with 100% certainty, but with very high probability. That's important distinction you want to make. We want to show that this dimension n is lower bounded. So as long as the dimension of the space receiving the data is bounded below by log of n divided by delta square, delta is a small number, the equation the inequality to 26 must be realized, and we now see that the receiving dimension is logarithmically related to the number of points and does not depend on the original ambient dimension d. So it depends on the tolerance parameter delta, it depends on the total number of points in the original space. It is not directly related to the ambient dimension d of the original space. This is a very important result. This result was proved in the mid-80s, and it remained within the mathematical community. In the early 90s, its application to data science was recognized, realized, and since then data scientists, computer scientists have utilized this framework to be able to bring about lots of improvement to this claim, and there is a huge volume of literature. I'm going to give you a glimpse of that growing literature, and this part of the literature is hardly 25 to 30 years old. So this is on the forefront of research in data science. So what is the proof? Let X be a n by d matrix, with Xij is going to be IID random from normal, unit normal, and we are going to define the mapping from Rd to Rn as f of u is going to be 1 over the n, m is n, 1 over square root of n times xu. Now please remember, u is d by 1. I am going to design my x to be n by d. So f of u is a vector of size n by 1, and we have assumed n is much smaller than d. So we are going to reduce the dimension, and this reduction is by the mapping f. Another specific thing that we need to realize is that this mapping is realized as a linear transformation, x. Linear transformations are easy to implement. So if xi is the ith row of x and u is not equal to 0, so let xi be the ith row of x and u not be equal to 0. Now look at this now. Xi, the elements of xi, each of the elements are from standard normal. The matrix is n by d. So xi is a random vector whose dimension is d. So you can think of this random vector to be a sample from multivariate normal distribution with 0 mean and covariance matrix identity of dimension d. Identity of dimension d. So if I took the inner product of xi with the normalized u, so denominator is the Euclidean length of u, I am going to normalize to be a unit vector. I am trying to take the inner product of xi with the normalized u, which is a linear combination of xij with the unit vector with the unit vector corresponding to U. Now please understand, Xi's are standard normal, the components of Xi's are standard normal. U divided by norm of U is U hat, and the norm of U hat is 1. So that means the sum of the square of the components of this normalized vector is all 1. Is all 1. And we already know every one of the elements of the row vector Xij are unit normal random variable. Therefore, if you look at the elements of this inner product, that looks like Xij, U bar j. So this is the linear combinations of all the vectors. Now you all remember, if you and Xij's are linearly independent. Therefore, the variance of this is equal to sum of the variances of Xij, U bar j, and the sum of the variance, the variance, now if you multiply a random variable by a constant, the variance gets multiplied by the square of that. So this is equal to summation U bar j square times the variance of Xij. Variance of Xij are all unity. Therefore, the sum of Uj's, the sum of the square of the unit vector is unity. Therefore, this sum is unity. Therefore, we can readily see that. Therefore, we can readily see this linear combination of multiples of components of the random vector along the ith row is clearly normal, and it is a unit variance. I want you to verify as a homework, but I have already given you basic ideas of the proof, and still is good for you to be able to write down all the details of the proof. Now I am going to define a new random variable y, which is equal to the product of xu, the square of the norm of that, divided by square of the norm of u. So here, what is that we are trying to measure? U, please remember, u is a vector, x of u is another vector. I am trying to get the ratio of the vector xu to u, the length of the square. So what is this measure? This measure is the measure of the amplification of the vector u by the transformation x. And this can be written as the inner, so this can be written as, you should know by now from matrix algebra, u divided by u whole square, because if I divide u by this, that becomes, I can pull it in, and that is equal to x u hat whole square. And x u hat whole square is something we have calculated earlier. So this sum, this random variable y is simply the square of the inner product of xi with a unit vector along the direction u. And we just saw these, each of the individual is a random variable. It belongs to 0. It belongs to standard normal, 0 mean, unit variance. If each of them are in standard normal, we are interested in the square. We are interested in the sum of the square. This must be n. I'm sorry, n must be equal to m. This must be n. n m, I can use anything, but I want to be consistent using n. So if there is a m, please change it to n without loss of generality. And there is no change between the argument using n and m. And these are chi-square variables with n degrees of freedom. We have already defined the chi-square variables. Chi-square variables are sums of independent, identically distributed squares of normal random variables. And that's exactly what we have proved for the inner product. So, apply the tail bound in 25 in section 18. Let's go back now. I have a chi-square random variable. We have already shown chi-square random variables have a special relation to the bound that we have seen so far. So, I am going to go. So, the example in section 18, chi-square variable, zk is normal 1. There are n independent random variables. So, this is an example of, as in the example in section 12, the sums of zk squared is a sub-exponential variable with two parameters, sigma and b, and sigma is 2 times square root of n, b is 4. I am now going to quote that result in doing what I want to do now. And I also want you to go back to the tail bound in 25 in section 18. So, let us go back once again to the tail bound. So, this is the tail bound. So, we showed that y, which is the sum of the squares of the standard Gaussian IID, is a chi-square variable with n degrees of freedom. This is not n, the n degrees of freedom. So, there, using the result in sub-exponential. So, when we deal with sub-exponential and sub-Gaussian, we did two things. One is a bound on the moment function and also a tail bound on the probability. This we have done all along. It is this ability to infer a tail bound using the bound on the moment generating function. There is a trick that is as old as Chernoff bound. So, even though we may be talking about Hopfing bound or Bernstein conditions, Chernoff plays a very fundamental role. So, I want you to keep track of two things. One, by bounding the moment generating function, we can also derive a tail bound on the probability distribution, and that is the trick. So, the tail bound of the probability distribution is given by inequality 25, and this is the normal random variable, and I am sorry, zk is a normal random variable. So, this is a centered, I am subtracting the mean of zk square from there. So, this bound is what we are trying to invoke. Please understand how the things are applied. So, we prove a general bound on moment generating function and probability tail for sub-exponential variable. We showed that chi-square variables are sub-exponential. We specialize those bounds to chi-square. Now, recognizing the images recognizing when I define the function f to be a linear map where the elements of the linear map are standard normal variable, 0 mean unit variance, we have now come to recognize the variable y here is a chi-square variable. If this is a chi-square variable, now I can apply the tail bound in 25. So, that essentially tells you that this chi-square, this bound is essentially less than or equal to. So, if this is m, that is m, if this is n, that is n. That is what I want you to be able to recognize. So, from the definition of f, what is f? F is the linear map, and rearranging the inequalities, this is simply square the norm of f of u by u minus 1 greater than or equal to delta, the absolute value greater than or equal to delta is less than this, is less than this. Therefore, now I would like to be able to recognize the following. This is when u is not equal to 0 and u belong to R of D, which is the original thing. Now, we wanted to preserve pairwise distances. Please remember now. There are n points. So, there are NC2, which is n times n minus 1 by 2 pairs of data points. And then there is a concept of what's called the union bound in probability theory. What is the union bound? The probability of a union of mutually independent events is less than or equal to the sum of the individual probabilities. That's what's called the union bound in basic probability theory. I'm assuming that you are familiar with the notion of union bounds. So, now considering the pairwise distances between the images, look at this now. F of ui is proportional to, except for the multiplying constant, x of ui. F of uj is equal to x of uj. Therefore, f of ui minus f of uj is equal to x times ui minus uj, and that is equal to f of ui minus uj. And that's what is in here. So, this is the distance between, the square of the distance between the images. Please go back to the picture. This is RD, this is RN, this is UI, this is UJ, this is F of UI, this is F of UJ. I'm talking about the distance between the two, So, the square of the distance in the receiving space is the square of the distance in the original space, that ratio. We want this ratio, please understand, the inequality 26, how did it go? The inequality 26 said that f of ui minus uj must be less than or equal to 1 plus delta times ui minus uj square. This is equal to 1 minus delta times ui minus uj square of the norm. So, if I divide both sides by the norm of that, what does this reduces to? That reduces to f of ui minus uj divided by ui minus uj square. That's the ratio that comes in here. So, this is exactly what this one here. So, this comes from here to here. So, the probability of that. So, here I am interested in the probability that it is lying between 1 plus delta times and 1 minus delta times. So, if I want to be able to compute the tail, it is outside of 1 minus delta, 1 plus delta. So, please remember, this is 1 plus delta, this is 1 minus delta. If this ratio is in between these two intervals, that's what the bound is. So, one way of trying to find what is inside this is to find out what is outside. So, this is 1 minus the probability of being what is outside. So, this is the probability not belonging to 1 minus delta, 1 plus delta. I hope you understand these are standard probabilistic arguments. Now, each of these bound, each of these in here e to the power of n, e to the power of minus n delta, let me go back, e to the power of minus n delta square divided by, so let me erase this part so that you can see this, e to the power of minus n times delta square by 8. N is the dimension of the receiving space, delta relates to the accuracy in the near embedding. NC2 is the total number of pairs. So, if I consider every possible pair, the random variable ui are independent. So, what is the probability that a set of mutually independent random variable, the union of them happens? So, I am interested for all I and j, for any ui uj, this ratio does not lie in the interval by union bound. This is the union bound. Must be less than or equal to, must be less than or equal to, go back. The 2 is from the original inequality. I am sorry, the 2 is from original inequality. The 2 is from original inequality. So, these two terms from the original inequality, this is the number of distinct pairs. The number of distinct pairs I am trying to add for each of these quantities the same. So, the sum is always less than NC2 times e to the power of n delta square minus n delta square divided by 8. This I am now going to simplify. So, this is where the conceptual idea of trying to ensure that it is very nearly isometric embedding with a very high probability. Where does the probability thing comes in? Because even though your original points u1, u2, u3 are given deterministic quantities, what could those uij represent? Please remember, when we talked about sources of big data, we have an RBG image. Each image, each frame is 250 by 256. There are 3 times 256. So, that's roughly close to 200,000. So, your D could be 200,000. What is the number of images? So, if you consider retinal images, I may have 1000 images, I may have 500 images. So, the number capital N is the number of images you have, and those images are deterministic, they are given to you, nothing changes, nothing random about that right now. But we are trying to map those deterministic objects into a random set of elements. So, f of ui is random because f is realized as a random matrix multiplying u. So, I am trying to map a collection of deterministic quantities into the same number of random quantities. So, when you talk about randomness, probability arguments come naturally into play. So, what is the probability that the pairwise distances will not lie in the interval? The ratio of the pairwise distances between the images and the original object will not lie in the interval 1 plus delta and 1 minus delta. It is the sum of all for all possible pairs, because I want all the possible pairs to behave in the same way. So, the union bound, the notion of the union bound comes in. So, NC2 is n times n minus 1 by 2. This is e to the power of n delta square by 8. This 2 gets cancelled, n times n minus 1 is less than or equal to n square. So, this quantity is what I am interested, and I would like this quantity to be very small. If this quantity is very small, means what? The probability that this ratio does not lie in a small interval 1 minus delta to 1 plus delta is very small. That means the probability it lies in the interval is 1 minus that, and I want this quantity to be less than or equal to epsilon square for some small epsilon. So, epsilon is the degree of approximation, that the degree of the quality. So, epsilon square must be greater than n square times e to the power of n delta square by 8. If I took the logarithm of both sides and simplify, I get this expression, which when further simplified becomes this, and this is essentially 2 times log of n by epsilon, log of n by epsilon. So, for all, please understand, these are all n's in my notation, these are all n in my notation, this is n in my notation. So, you can readily see the dimension of the space receiving must be at least 16 divided by delta square times log of n over epsilon, which can be seen that is lower bounded by log n over delta square, log n over delta square. So this is the transition from here is simple mathematical argument. Therefore, what is that we have shown? If you are trying to map a set of n points from a larger dimensional space to a smaller dimensional space, the dimension of the receiving space must be at least as large as log n divided by delta square. And this jives very well, because we showed that you cannot map an equilateral triangle in 2D to 1D while preserving pairwise distances. So exact isometry is not possible. Even near isometry in that case is not possible, because if you have a triangle ABC, each of side unity, if you map into A, B and C, the distance between BC is 2. It is not essentially 1 plus epsilon. So I can't even allow this. The epsilon is essentially 1 in this particular case. I'm sorry, delta is already 1. So this is called expansion. So in this embedding, the pairwise distances cannot be preserved, and there exists at least one edge or one side of the triangle that receives an expansion by a factor 2. So this is clearly an embedding. It's not isometric, it's not near isometric. So when you go from high to low, you may have to give up some distances, but I would like to be able to control the maximum increase in the pairwise distances, and that's where the quantities epsilon delta come into play. So because of counterexamples of this type, we do see that unless the receiving space dimension n is at least large enough so that when trying to squash a number of objects from high dimensional space to low dimensional space, I don't have to bring about too much increase in the pairwise distances. And that essentially, that's one of the reasons why the reduction from 2 dimension to 1 dimension or 3 dimension to 1 dimension, the embeddings while preserving the distances do not exist. That's the reason why we compromise on near embedding, near isometric embedding. So there are lots of interesting ideas here. Impossibility of isometric embedding when you go from high to low dimension. So trying to find out what is the minimum value of the size of the space in the lower dimension that could accommodate near isometric embedding. So this is the best result one can think of. So this result was established in the early 90s. Now this result has been extended in several different directions, where the constants of coefficients of the lower bound have been improved. So you may wonder why we did measure concentration. 2 reasons. One, we said that when you go from low dimension to high dimension, distances are concentrated, measures are concentrated. Distance concentration, we use certain kind of probabilistic argument to show distance gets concentrated. We also showed certain probabilistic argument to show the pairwise distance can also be preserved very nearly, and for that we needed tools. The tools relate to different bounds relating to quantifying measured concentration. So now you can see how probabilistic argument, Chernoff type probabilistic argument play a very fundamental role in data science, especially dealing with high dimensional data. Now, I would like to summarize the properties of sub-exponential random variables. Please understand, this dimension reduction, which is one of the fundamental applications in data science, is made possible by the definition of sub-Gaussian and reduction to sub-exponential. So you can see the importance of the notion of sub-exponential. Also, the property of chi-square variables being a sub-exponential variable. So we proved this for a general sub-exponential and derived the Lindenstrauss lemma relating to embedding as a corollary. Is this the only way to prove? Now there are probably several different ways of proving this. This proof is also conditioned on the fact that the distribution of the mapping f of u is equal to 1 over square root of n times x of u, x the matrix, and we have assumed xij are normal 0, 1 IID random variables. Now, is normal random variables are the only one using which you can have a linear mapping? The answer is no. There are lots of other modifications have come about. But before we talk about some of those things, I would like to first summarize some of the important property of sub-exponential variable. If x is a sub-exponential variable with mean 0, then the following conditions are equivalent. So, there exists two parameters nu and b such that the moment generating function of the random variable x is upper bounded by e to the power of nu square lambda square by 2 for absolute value of lambda to be less than or equal to 1 over b. This is the restriction. The second one is there exists a C naught such that e to the power of lambda x is less than infinity for absolute value of x less than or equal to C naught. Then there is the tail probability coming from the moment distribution, coming from the bounds and the moments. The tail probability, so the absolute value, the probability of the absolute value will exceed t is less than or equal to C1 times e to the power of minus C2t. It is this tail probability which is a direct consequence of the upper bound and the moment generating function is the tool that we have applied. Please go back. Measure concentration relates to tail bounds. I want tail bounds which are very good. To get good tail bounds, we have to deal with moment generating function. That's an idea as old as Chernoff. And Chernoff bound is at least as old as 1950s. And the another one is the supremum, which is the maximum over k greater than or equal to 2 of the ratio of the kth moment of x divided by factorial k. The kth root of that ratio is finite. So this is a kind of a result that relates to the rate of growth of moments of sub-exponential random variable. You can see Bernstein's condition relates to bounding the kth moment for every k. So there are lots of beautiful probabilistic results that are involved in here. All these are equivalent. In mathematics, it is not unusual to express results like this. Then how they will prove this? They will first prove 1 and then say 1 implies 2, 2 implies 3, 3 implies 4 and 4 implies 1. That's a standard technique in mathematics. So if you are mathematically inclined, I very much urge you to be able to verify these equivalent conditions. We have given a set of 4 equivalent conditions for sub-Gaussian as well earlier. So it is the collection of these results that provide you a very good background on measure concentration, and measure concentration plays a fundamental role in dimension reduction in data science. With that, we conclude our exposition of this module, measure concentration, I know it is a little bit more mathematical, but those of you who are serious about your work, graduate level work in data science, should catch the bull by the horn. You have to face the mathematics and understand it, appreciate it, so that you develop good skills in applying tools from probability theory to your problem. Thank you.